What I wanted to talk about today will be a short introduction to simplicial models in distributed computing, which is a topic in the larger framework of topology of knowledge, or topology of information exchange, where we try to create simplicial models for answering questions about, for example, coordination of different agents, or more generally topology of knowledge. So just before I proceed with the distributed computing, let me say a few words about the old stuff which we've been doing before going to distributed computing, which was the combinatorial algebraic topology. The reason I want to mention this is because it turned out to be an area which really found its applications in the theory of computation later on. And this was an area which we developed, where in contrast, also actually quite in parallel to what Gunnar said in his talk, to the classical topology where things are not necessarily computable, we really concentrated on combinatorial things where computation is the key, but also the description is in terms of language of combinatorics. So not only we could compute things, but also there are a lot of combinatorial creatures crawling around, which make, for example, things like spectral sequences much easier to deal with than in general context. Just as a few words, because this will be the kind of cell complexes which we will also have in the distributed computing. All of them will be simplicial complexes, and their names, there will be names for all of the simplices, and also there will be combinatorial procedures for taking the boundary. So not only it's necessary to name the things correctly, but also it's necessary to describe correct algorithms, what it means to take the boundary, which goes beyond just the usual simplicial. We just take this as a boundary simplicity. Since they all have names, the rules are actually quite complicated descriptions of how to transform description of simplices into other descriptions of simplices to find out which one is on the boundary, before we can then proceed with some of the standard combinatorial techniques to actually understand the topology. So this is something which now almost 10 years ago, which we looked at, which was this combinatorial, and in more modern developments, more recently, we've been applying this to distributed computing. Okay, so let me maybe say a few words before plunging into finer technicalities of the models. What's going on here? So classically, you had, so in the 50s or in the 60s, when people started to build more complex networks than they used to, they needed to have theoretical models. So the first classical theoretical model for distributed computing was a peer-to-peer communication, where you would model the network as a graph, and the agents would be nodes, and they would be simply sending messages to each other. Now you also have time uncertainty in this model, so you would have to have rules like, if A sends a message to B, and then later he sends another message to B, then you have to be sure that the second message arrives after the first message. That would be one formal property you would require. But you would never, if you wanted to actually answer questions about what's going on in real life, you wouldn't be able to say the following, which you would want to, but it's not what's going in real life. So if A sends a message number 1 to B, and then later he sends a message number 2 to C, it may well be that C sends this message and it arrives earlier than the one you send. Okay, so this can happen. Even though you, as an agent, actually send them in the right order, since it went through another one, it may actually mess up the order. And a priori, you wouldn't be able to tell what will happen. All you can do is you can send messages, and you have a set of formal rules, and all you know is that your model will appease a set of formal rules. Okay, so you can have different rules for different models. This is one thing which is quite different from many of the contexts in which mathematicians work, where we have very few and agreed on models. They actually have very many models, and you can assume that the message you send will arrive eventually, or maybe you don't assume that. You can assume that the person will be always active. You can assume he might be not active, which means the node has died. You may also assume that if he is active, he's always sending the correct information, but you could also assume that if he's active, he may get corrupted and start sending the wrong information. So you have to develop all sort of algorithms under time uncertainty, which is, so usually they wouldn't call it algorithms, they would call it protocols, to deal with all of this, okay? And the more uncertainty you assume, the more complicated things get. Okay? So, in the very beginning, people started to think about how to organize these things, and it turned out that that even some of the simplest tasks, so they would have a number of standard tasks. This is how the theoretical part started to develop, because the realization was that there are standard tasks you want to organize in your system, which are provably theoretically not solvable under the constraints that you are imposing. Okay, so it's a little bit like maybe analogous to Arrow's impossibility theorem or something like that. So you would make no strange assumptions. You would just want to say, for example, a task you would want to solve would be, I don't know, you have n agents, each one starts with 0 and 1. In the end, you want them to agree on one value. Okay, so, and you want to have an assumption that if everybody has a value 0, they agree on 0. If everybody has a value 1, they agree on 1. If they have different values, you don't care, as long as they agree on 1. Okay, and it turned out that in completely standard models, this task, which is called the binary consensus task, is not solvable. Okay. The proofs of this in the 60s and the 70s were done by several teams of people. This is all done with using graphs, because they would model, like I said, the communication by graphs, and they would have very complicated arguments showing that basically there would be very tedious constructions of malicious execution. Okay. So in distributed computing, different from consecutive computing, we do not have one execution, we have a totality of executions, right? Because you just have n agents, they start doing something at the same time, and you don't know, they're asynchronous, you don't know what's going on, so there is maybe a certain set of possibilities which will happen in the end. Basically, who goes first, with it roughly, okay? And when you're designing a protocol here, what you want is that something which will work no matter what execution you have, or you prove the possibility. Okay. And there turned out to be a certain limit to what you could prove using graph theoretical methods. And jump forward in the 80s and the 90s, there was more understanding that using simplicial methods would be able to push the boundaries of what we know about the communication and coordination between different agents. So, so how do we kill this?
Just put enter.
Huh?
Enter.
Okay, but not on OK. Okay. Okay, so yeah, so like I said, in one of the models there are malicious agents and they do things to you. Right. Okay, so roughly speaking, this is the general idea behind this whole business. Okay, so now and then more lately also there's people. So like I said, this was a classical model which people actually don't work that much with anymore. It turned out that more amenable to a simplicial methods is the model, so-called shared memory model, where you have agents and there is a common memory, and they execute things like the write to the memory and the read from memory and so on. So one of my co-authors, Morris Herlihy, he is so all of my co-authors are computer scientists, and one of them is also every now and then spending time with Intel and so on, who are actually manufacturing chips. And this is a very hot topic of research, because you need to understand what atomic operations you need to implement in order for your model to be. I mean, you don't want to build a chip which can fundamentally not solve certain tasks, just because, theoretically speaking, they are not solvable in this model. And at the same time, it's quite costly to implement atomic operations atomic operation would be an operation like read from memory, write from memory. But there will be more, so for example, this would not be sufficient. You would need to implement more sophisticated one, which would at the same time read and check some parity or something like that. And there's a balance between costs of implementing them and making sure that the model will actually be able to do computations effectively. Alright, so this developed for a while, and we decided to take a little bit more broader view of the subject and develop a little bit more theory, not for the theory's sake, but in order to encompass the existing models, and also to make accessible a variety of proofs which are each phrased in different language, but once you translate them to the abstract setting, they may turn out to be actually very similar, if not absolutely the same. So you can associate a simplicial complex in quite very easy ways to start with. There's a number of them associated to this setting. So the first simplicial complex, which is people can construct, is so-called input complex, which is simply a simplicial complex of all initial configurations. Okay. So let's say you have n processes and n agents, and each has a certain inputs, but maybe these inputs are correlated. So for each set of inputs, there are certain sets of inputs which are allowed. You can model this as a simplicial complex. Okay. By itself, it's not much, but it will help to do things. So for example, if you, for example, in binary consensus, that would give you a standard simplicial sphere, but there could be other things. Okay. So for example, if it's n agents and each one has value 0 to k, then it's just a join of n sets of k points, which is a topological space. It's not a manifold. It's well known to be homotopically equivalent to wedge spheres. You can think about that. But then it's also a question of what properties exactly of the spaces will actually be relevant for this context. So another simplicial complex you can associate is the output complex, where you allow final configuration. So for example, in the binary consensus problem, that would just consisting of two simplices. One is all zeros and one of all ones. Okay. So basically, roughly speaking, well, I'm going to get to this. Okay. So more interesting, or rather central actually, is the simplicial complex of all executions, which is called the protocol complex. Okay, so what is a protocol complex? So the protocol complex is okay, so you have a, so like I say, so you don't have one execution, you have a totality of execution. You could see it as a set, but you could also try to associate a topological space associated to this set of all executions. You would want to have higher dimensional simplices corresponding to possible execution threads. Okay? And then you would want to glue them together, and the lower dimensional simplices would correspond to what subsets of processes see. So in the standard model, which I'll describe in a moment, there's this theorem which, for example, which computer scientists don't understand why you need a theorem like that, but mathematicians would immediately understand why you need a theorem like that. And the theorem says that if I have n processes and they've run a protocol, and their views are the same of what happened. Each one has a view. Okay, he runs. I send 5 to this guy. I got 3 from it. Whatever. It's a view. Okay, and the theorem says that if all of their views are the same, then it is the same execution. Okay, so of course it is the same execution. We'll say any computer scientist. But in fact, if you think about it a little bit more, you will be very easily construct a lot of different communication models where the agency is the same locally, but it actually corresponds to a different execution. Okay, so that's something which we need this installed model. For example, if you want to develop this theory, you want to say this is maybe an assumption you want to have, such a kind of thing. Okay. So, like I say, so the vertices in the protocol complexes are the local views of processes. Okay, and the top-dimensional simplices are actually executions, or if you want, in the model, it's totality of views of the coherent views. And lower-dimensional simplices will be you know, views of subsets of simplices. Okay, and the things you say about simplicial complexes will correspond to what's going on in the communication model. So, in the very simplest case, if I have, for example, 2 processes and each one simply writes let's say it writes to the memory and then it reads. That's his, okay, so then there are actually three possibilities of what can happen. Either the first process will do all of his writing and reading, then the second one will do that, or the other way around, or they will do it simultaneously, right? They will write both and read both. Okay, so there are three different executions, and for example, there are different views. So if the second process sees both values, then, well, let's say he only sees one value, that means it's his own value, then he knows what the execution is, because he knows that he was first. But if he sees both values, he doesn't actually know what the execution is, because he doesn't know if the second guy saw his value or not. Okay, so in the simplicial setting, that would correspond to a vertex which is adjacent to two edges corresponding to the two executions. So you have top-dimensional simplices modeling executions, and they're glued along lower-dimensional simplices if the views of the sets of processes are the same. This is the geometric model. Phrased in this geometric model, a lot of old arguments which computer scientists had, which would go on for 20 pages, concerning a malicious execution, would boil to like two-line proofs saying what you want is to construct a map from a equivariant, a sphere with S2 action into something which is lower dimensional, disconnected. That's not possible. There's abstraction to that. End of story. Whereas they would have to go many pages with mistakes trying to construct these executions. But they would just boil down to, for example, some sort of abstractions, fixed point theorems, and so on. So there is a good value of phrasing this in this language. Of course, to describe these tasks, there in a standard setting, there is so-called task specification map. So this means, this is what I said very quickly, verbally, things like, if they all have 0, then they must decide on 0. So the task specification map simply for each input gives an allowable set of outputs. Okay, so like again, there's not one output, but for each input there is an allowable set of outputs. Which means we do not have, if you want to model the simplicially, we do not have a simplicial map, because a simplex will not map to a simplex. A simplex will map to a subcomplex of possible outputs. Okay, so therefore we're forced to work with carrier maps. And then there is another map, which is called execution map, which goes from the input complex to the protocol complex, which takes every input and maps it into the subcomplex of possible outcomes, possible executions. And there is a simplicial evaluation map from the output complex, from the protocol complex to the output complex, which means that it simply assigns the output value for each execution at the end. And then, when you have all this language, you can actually phrase simplically what it means that the protocol solves the task. So you can define all these things simplically, and you basically come up to saying something like the protocol solves the task if a certain diagram commutes. Now it's not going to be a diagram of simplicial maps, it's going to be carrier maps, so commute will mean that it's in the inclusion instead of equality. Okay. But roughly speaking, what I'm saying is that you can construct a formal framework which will model the distributed computing, and the little benefit of this will be that once you have it, you can phrase even the open questions from distributed computing purely in simplicial setting. There is no more mentioning of algorithms. It will be just questions about existence of certain maps between simplicial complexes. Okay? Or maybe even simpler than that. So I think I will get to at least one question like that, which is also open, but this is the general idea. But it doesn't mean that these questions are simple. They just, usually in fact, they may be not the ones which have been studied. So, okay, so like I said in the beginning, there are many different models for communication systems. This is a complexity which a mathematician has to face if you try to work in this field, because there is not one, there are a lot of different models. Well, fortunately, there are also reduction theorems. So there is basically an equivalence class of models which have the same computational power. But just to give you an example of what these models look like, here's one example which is in our book called Layered Immediate Snapshot Protocol Model Complexes. And just to go, I mean, you can see that there are a lot of things one can tweak, but that's the one most people use. So you have processes which communicate with shared memory using two operations, which one is write. So he writes its state to a certain devoted register. Each process has a devoted register. And they have a snapshot read, which means the process reads the entire shared memory in one atomic step. So if you want, you can think about it as a mailroom model, where each process goes into the mailroom and he can deposit things in his box, or he can look at what's in the boxes. Okay. But there's a difference with the mailroom model is there could be several people in the mailroom at once and they don't see each other. Or at least they don't communicate to each other. In fact, this is a standard model in my department, but most of the time if you see somebody in the room, you communicate to him, but here not, okay? So it's like, they're accessing, if you want, I don't know, airplanes accessing flight tower and each communicate with it, but they don't actually see the other guy what he's doing. He may be reading the information at the time, he may not be reading the information, and I will have to make decisions under uncertainty. And my decisions are better be right. Okay. I don't know how quick he is, he could be slow, he could be quick. He doesn't respond, he could be dead, but maybe he comes later, I don't know. This is a model usually used when you're trying to find a referee for the paper. You don't know if he's slow or dead, but this is a standard model here. And you have to make these decisions, okay? So you basically have to have maps which satisfy certain conditions. Okay. So in this model we allow crash failures. But for example, we do not allow so-called Byzantine failures, which means that there will be malicious communication. So either the guy is dead or he sends the correct information. The Byzantine failures are quite difficult to deal with. Most of the time, if you want to deal with that, there will be some sort of majority voting in the network to deal with malicious failures. If the majority is healthy, then overvote, outvote, as So, and all the protocols are synchronous, they're wait-free, which means we don't wait for the guys. If they're slow, we have to make the decision. There is no upper bound on how long it takes to execute a step. And then there are some technical assumptions to make topology nicer. So this is kind of an interesting thing, which I may be able to illustrate quite quickly here, that the more natural model you take, the worse is the topology. So the most natural model you would take would be everybody just reads and writes from memory. The topology of this is not even clear what's going on. I mean, you can create a model, but it will be very complicated space. Whereas if you assume some technical things, you will not lose much computational power, and the topology will be quite nice, because you will end up with some subdivisions of simplices. So, immediate snapshot model is such a model, where you, in addition, you assume that each step of processes group becomes active at the same time, and they read and write together. They're not allowed to interleave. And also that the whole execution proceeds in a certain set of rounds. So here is the topology which we see if we assume these additional things. So for example, this here, very important picture consisting of 3 intervals and 4 dots. This models the situation when you have 2 guys and they communicate once, so each one writes and reads once. So like I said, so for example, here is this node, and it means it's process 0, and he sees both values, which means he sees that he has written something and the other guy has written something. So there are 2 executions which can correspond to that, right? Whereas if he only sees his own value, he knows which execution it is. Okay, so that would be a model which for this. If you go to 3 processes, then you see a picture like that, where each vertex corresponds to a view. So if you have 3 guys and they each write and read once, the view of each process is simply a set of what he's seen. He's seen himself and maybe someone else. Okay, so there are 4 possibilities for each guy, so it's going to be 12 vertices. But there's going to be 13 possible executions, okay, because this will be strings of write and read, under a little technical condition of interleaving. So it's actually very easy to calculate the number. It's a certain version of Bell number of this number of execution, which grows very rapidly, but for 3 it is going to be 13. So in fact, I got an email from a topologist, Peter Landweber, who has read this book, and he said that this is a very interesting picture, and because it also occurs in some, it is called also Tom subdivision, and one has to investigate what the connections are, but we don't know what the connections are. It is the most natural thing to do, as opposed to the barycenic subdivision in this context, if you want to preserve the colorings. Okay. So if I want to put, and these things are naturally colored, it comes with the model, because each vertex is a view of a process, and each edge connects to compatible views. So each edge means these two guys can have, there is an execution under which they have these views simultaneously. Now if you simply color with the identities of the processes, this can be colored. So for 3, I can only get away with 3 colors. Of course, if I proceed with barycenic subdivision, I will have to introduce the 4th color in the middle, so this will be ruined. This is the way to go if you want to subdivide, like you do with the barycenic subdivision, at the same time as preserving the colorings. Okay. So this is why we call the standard chromatic subdivision. And here it is not an artificial construction, it's a very natural construction, and iterations of this subdivision correspond very naturally to simply executing the protocol in several rounds. Okay, so this comes very naturally here. So this is supposed to illustrate why we want to have this model which has a little technical conditions, because the picture is very nice and occurs in other places in mathematics. A lot of things are understood about it. There are some open questions about this picture which I will phrase in a second. But if you don't do that, and if you don't assume the technical conditions, but if you stick with the model as close to reality as possible, you will end up having, so let me skip the proofs of that. So for example, if you skip the condition of being layered, okay, you just say, okay, they execute, we don't request them to execute in rounds. There will be much more complicated description, let me skip over this, much more complicated description of the simplices. You can still get combinatorial description, you can always do that, but it will be increasingly complex, and the topological pictures will become more complex. So nothing will change that picture, but if you have 3 processes, for example, there will be additional executions. There will be 6 additional executions which you didn't allow before that, where you would have things like you have the first process right, and then the second process right, and then the first process read, and then the third process right. So the third is not allowed to come. They have to go in groups. But if you allow that, there will be more complicated executions. And if we are operating under this general model of implementing each execution by simplex, then we are forced to glue in 6 more triangles in this picture. Thereby we will not have any more subdivision with simplex. We will have a different space. And it's growing. It's quite complicated. The problem is also if you repeat the rounds, it will not anymore be iterating in the same topological space, but it will be just a family of simplicial complexes which will be evolving somehow, and will be quite complicated. So one could try to understand more about that, but since on the distributed computing side, the equivalence theorems of computational power, we may as well stick with the model which is topologically the simplest, since it anyway yields the same power, same results. Okay. But you will quickly end up with a family of complicated things. Still people work with that, so this is a theorem which I proved, which is only for 1 round, and or if for 2 rounds we don't know, but if it's for 1 round we know, if for n processes. And you can also go in a different direction, and so recently people went in the direction of this Benevides-Reisbaum, where they have only, well, this is actually 2 processes should be, whereas you only look at what's going on with two processes and do multiple rounds, you get graphs, but they're quite complicated. And they prove that you get collapsible spaces. All right. So if you remove all the conditions, even the snapshot condition, just then you will have spaces like this, which so this is a, so this is a middle ground. So so you have this once, and in this case you have to subdivide more, but it is conjecturally subdivision of a simplicial complex. So if you want, in one case we know it's a standard subdivision and it appears apparently in a lot of places, so I learned. In another case we have no idea what's going on, we don't have a manifold, and here we conjecturally have a subdivision of a simplex. There are a lot of things people understood about that. It's very easy to prove things like it's a pseudo-manifold and things like that. Anything combinatorial is very easy to prove because you just check if it's condition. Since we have a complete combinatorial description, we can very quickly check. But to show that it's a homeomorphic, that it's a subdivision. So actually we can even show homeomorphic, but it's a subdivision, linear subdivision of a simplex. That is probably true, and it's true in all the cases people could compute, but cannot compute that, cannot prove that at the moment. So I wanted to maybe get to, so it has some interesting structure. So, so I don't know, maybe I should just summarize this by saying, so we have this book about this where a lot of these things are written up. It's not that new, but it's a few years ago. So maybe let me summarize this part of the talk. We have simplicial methods, and in this, at least we have seen that they are useful for the distributed computing. And initially the idea was to provide a rigorous foundation for this interdisciplinary area. I have to say maybe here that there was real need for that because there were also things which were wrong. So there were things which computer scientists proved, whatever that means, and later they were deemed to be incorrect. And not only the proofs, but in fact the statements. So in fact I will see an example of this in the second part of the talk. So the more of these things happen, because people just write things up, 5 pages, 7 pages, conference submission, never a full version, and then things turned out to be really wrong. The more people understood we really need rigorous, checkable foundations for this. So this protocol complexes provide a very nice setting, and they are a kind of configuration spaces for all possible executions of protocols. And for different models, the combinatorial topology of protocol complexes can be completely described in the combinatorial language of graphs and all that, but it can be quite sophisticated, and at the same time it will contain answers to the computational questions. So that's quite an interesting field to look at, because you have complexity and at the same time it is highly relevant. So a lot of times when you make up this model, you have a choice: should I make a nice model or should I make it realistic? And we really try to stick with realistic. Whatever we get out in the end actually has to do with something, but it also inevitably leads to more complicated things. And it leads to new and interesting mathematics. Now, so maybe references I'll skip. So what I want to talk about in the remaining time is to look at one specific question which is highly relevant in distributed computing, and at the same time can be formulated purely in terms of simplicial complexes. In fact, purely in terms of well, not exactly this simplicial complexes, but simplicial complexes like this one. Okay, by this I mean for more vertices. So this one is for 3 vertices and iterated. Okay, so there are many ways to describe this complex. I can describe one offhand, which is kind of maybe the easiest to understand, but maybe a bit painful to prove things about. And that's simply that you take the Bedlewo subdivision and then you blow up each vertex a little bit. So for example, there should be a vertex here in the middle, or you just make it shifted a little bit and give it different colors. Here there should be a vertex in the middle, you just shift it a little bit and give it different colors. You shift it away You have a red one, you shift it away, you have a red one here. I think that's the easiest intuitive description. That's not the mathematical description exactly, but that's what's going on. If you want to go to a simplex, you have a vertex in the middle, you'll just give a little simplex, and if you twist it right, you'll connect it and it will be fine. Okay. Alright, so there are different ways, simplicial chromatic joints and all that to formulate it very, very clearly and give it a specific description, but I think intuitively this is the right way to think about the subdivision. Okay? And now you can do it A for any set of vertices, and B you can iterate it. Okay. All right. Now here's a thing which I think is the easiest from a topological point of view to understand, is the following. So what you can do also is the following. So you can associate to this, well, I could say semi-simplicial set, but since I grew up with Hedge's book already, so I prefer to say the delta complex. So there is a unique a delta complex which has one simplex in each dimension. Of course, there are no simplicial complexes like this, but there is a unique one where you know, you have to, in order to obtain it from this one, you have to take these vertices, identify them to one vertex, and then you have the edges and glue them in this direction. So this one, so you have to say this is 1, this is 2, this is 3, and then you glue 1, 2 to 1, 3 in this direction, and then 2, 2, 3 in this direction. So here you will get the dunce head. And this you can do in all, right? So you can take a simplex. So a formal way to say this is that you have a simplex, and you just identify any two boundary simplices of the same dimension in the right order. Right? The vertices are ordered, because we are doing delta complex. The vertices are ordered 1 to n, if it's an n simplex, n plus 1. Right? So any two boundary simplices, order the vertices and identify them. Okay. This will give you a family of spaces, circle, here it will be a dunce head, and so on. Okay. And this subdivision, which we are doing in distributed computing, you can do it there as well, because it is, you see, you can, this can be glued on this one, because the way subdivision is done. Okay. And now you can look, this is going to be the space we want to look at. So we want to take that space and look at the iterated chromatic subdivisions on this, if you want, delta complex, unique delta complex with one simplex in each dimension. The other way to formulate it would be that we will want to iterate the subdivisions simply of the simplex, but then put values on the vertices, and to compensate for the lack of gluing, we would have to impose, this is how it's done in distributed computing, they impose conditions on coherency of labels. So for example, they would say each of the corner vertices should get the same label, whereas I would just glue it to one vertex. So there is a standard task, which is not so well understood, which is called weak symmetry breaking. Okay. So in this task, what you have is you have n processes. Each one has a certain process ID, and that's it. And then they communicate, and what you want to do in the end is that they want to be divided into groups, so that each group there are two groups, and each one is non-empty. So this is called weak symmetry breaking. Each time they communicate, they just compare their IDs, and they're only allowed to use the fact which ID is bigger, so they're not allowed to use the numerical values of IDs for them. Okay. So, in particular, in this model, if I execute alone, and I never see anybody, I should make my decision no matter what my input value was. Okay. So that would correspond to saying that the values where I associate the vertices are the same. Okay. If, for example, I have 3 processes, but only 2 are actually participating, then whatever they do should only depend on the the relative values of their IDs, and not on the numerical values. So in particular, if 1 and 2 executes, which would be this edge, or 1 and 3, they should do the same. Okay? So this corresponds topologically to gluing this edge to this edge. So, the model is, like I said, the standard chromatic subdivision, and dual to this, this is actually their original model, this flip graph, where each vertex is their execution, and the edges connect executions which are compatible with all. So you would have this picture here. And the standard chromatic subdivision, like we said, it can be applied to simplicial complexes in general, not just to a simplex. It can be iterated, therefore. And what I just said, but formally written out, if I have any two boundary simplices of the same size, there is a linear isomorphism identifying those two simplices, and the subdivision can be done on them. Right. So, for example, if you have a triangle and you iterate this once, you will get the blue picture here. It's a distorted triangle because it's kind of painful to draw it on the triangle itself, and the black one is a dual graph designed. So that's, if you want, the picture of what you see if you have three processes executing at once. Just as a picture. Okay. So now, how do we model this weak symmetry breaking task? So the simplicial formulation is as follows. Take the n simplex, take T's standard chromatic subdivision. So take the simplex, iterate the subdivision. Okay? And then they make a decision. So each vertex now is the final state. So you want to put labels 0, 1 because they're distributed into two groups. And like what we said, this should be compliant, meaning that it should be constant under these identifications. So depending, you either formulate it this way for the simplex, or you skip this condition, but then you're not subdividing the simplex, but the delta complex I was talking about. Either way, it's the same question. Okay, so this is the question again. So if you want, you can do it for a triangle. Okay, so you go to the triangle, back to the triangle. Okay, so take the triangle. This is t equal to 1, okay? But I can have t equal to 2, or maybe I don't want to because we've seen the picture. It's quite cluttered. But I can take the subdivision and iterate it as much as I like, okay? And now I'm asking the question, can I put values 0 and 1 on the vertices of this iterated subdivision so that the following two conditions are satisfied? Condition number 1, the three corner vertices have the same label, okay? Since it doesn't matter which 0 and 1, I can as well just assume I put zeros on all the corner vertices and pass on. Okay. The second condition is that, well, actually three conditions. The second condition is that on each edge, the labels are coherent, which means if I read the label starting from here, going there, along this edge, I'm reading the same sequence as reading from this vertex to this vertex, and I'm reading the same sequence as going from this one down. Okay. So in other words, I could just put the labels on one edge and then on the other two they would automatically be implied. Okay? And the last condition is that there is no triangle where all the labels are the same. Okay? That's it. That's a question. Okay? Does there exist such a T number of subdivisions of this so that this is true? Okay? If I took one step back, which is a bit difficult with these slides, I'm not sure I should even attempt. Okay, but okay, this is n equal to 3, but the other picture I'm trying to remind you was the interval, which was subdivided into 3 parts, right? Oh, maybe I should go back. Where was this? Let's see. There. So if I took one step back, my question would have been, I have an interval, this is a subdivision. Subdivision means I put two vertices, okay? I can iterate it, which means I put two vertices here, 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 and so on. Okay, can I put now the labels 0 and 1 so that no interval has the same labels and the values on the edge, on end vertices is the same, okay? The answer is no, because no matter what t is, the number of intervals will be 3 to the t, which is an odd number, and since my condition says I should change the label each time, I'm not going to start with 0 and go to 0 in odd number of steps. End of story. Okay, very easy argument, but that already proves like a 20-page argument from the computer science, which they had to do. Okay, but this is okay. The next step, what about 3 processes? Can I do it for 3 processes? The answer is no, but it's a more complicated argument. You cannot just go from one to the other. You have a triangle to deal with, right? And you have a lot of things. But the answer is no. Okay. So, which means that formulating that other language, that would say that, that would say that, the other way to say that would be weak symmetry breaking is not solvable for 3 processes. That's the same statement as saying it's not possible if you have 3 vertices. The one with the interval is weak symmetry breaking is not solvable for 2 processes. Okay. So actually, there was a theorem proved which said weak symmetry breaking is not solvable for n processes. Okay. Turned out to be wrong, unfortunately, and that was the interesting part. That's where the part started in this theorem. So there was a theorem by Herrlich and Shavit, which said that you cannot solve weak symmetry breaking for any number of processes. End of story. Very standard theorem. There are a lot of theorems like this in computer science. You cannot solve it. Turned out it was wrong. They tried to use a fixed point theorem from topology in an incorrect setting. It only works, it only can be used if the number of vertices in the original simplex is a prime power. All right. So, in other words, if you want to be a diplomatic, as I would like to be, you formulated the positive theorem saying that if the number of vertices is a prime power, then that does not exist. So, for example, cases 2 and 3 are covered by this, and case 4 is covered by this, case 5 is covered by this. So the first case you would ever hope to find a counterexample would be 6, which is a large number, because we've seen what happens if we iterate twice in a 3, and then we have a 6 vertex, it's a 5 simplex, and then you have to have iterations, and you have to have a lot of them, because you can actually prove that in 1 you will never be able to solve. So it's a question, does there exist T? The reason you have to formulate a question like this is because you're asking, does algorithm exist? Now, algorithm contains a certain number of rounds, so you should say, does there exist T? Does there exist number of rounds? You don't want to ask for 1 or 2, because, okay, you cannot solve it in 2 rounds, big deal. Okay. So it turned out that their proof only works for the prime power. And the reason is, well, I don't want to get into it, but they come down, it boils down to a certain identity of binomial coefficients and some divisibility conditions and so on, and you get an abstraction in the story. So there is actually some cohomological abstraction in the background, which they don't want to hear about, but that's what happens. And for a long time, people actually thought that that's an artifact of the proof and not of the fact. So they said, okay, big deal, cannot prove it for all n, with some strange mathematical method, but of course it's true. I mean, look, if you have a task, okay, a distributed task, n processes, okay, and I know I cannot solve it if the number of processes is a prime power. Well, of course I can never solve it for other numbers. Why should I be able to solve it for 6 processes, not for 5 or 7? I mean, that's a completely weird situation, right? I mean, it's not like I'm doing something strange. I'm just saying they talk to each other, they want to agree on 0 and 1. I don't know. Why should that be the case? It turned out, to a big surprise, that actually it's not the case. So there was another theorem later, proved by a group of Mexican computer scientists, Castañeda and Reisbaum, which have, to a big surprise to everybody, actually constructed, sorry, this should be a prime, that when it is not a prime power, then they did prove that you can solve it. In other words, you can put labels on the subdivision. Now, they don't have an explicit way. It's an algorithm which just proves existence and converges to something. So, in particular, it's very hard to estimate what is the number of t, which will be the number of rounds. How many times do you need to subdivide until you can actually put the labels? That's the question. And people try to do research on that. So there would be a super exponential bounds. So for example, the bound would be n to q plus 5, where q is the largest prime power dividing n, which potentially could be basically n, close to n. So it's a very large number of rounds, which would be an enormously large subdivision. For example, for 17 subdivisions, that's a very big number. You only have a lot of simplices if you think about it. I don't even know how many digits that would be, maybe 50 digits of simplices, because it goes to the 17s and each one has tons of. So it's nothing remotely clear what's going on. Now it turned out that the following strange result is true, which I proved. which is the following. So assume that we have a binomial identity. So by binomial identity, I mean that sum of some binomial coefficients is equal to some other binomial coefficients with the following conditions. So I have, so n is some number, okay? Let's say n is 6 or whatever, number of processes. Okay, so then I sum some binomial coefficients here equal to sum of other. Okay? So the only condition is that I have n choose 0 on this side, and I don't have n choose 0 on this side. Here I n choose 1, and I don't have any n choose n anywhere. Okay. So let me give you an example of a binomial identity. So for example, if 6 choose 0 plus 6 choose 3 is equal to 6 choose 1 plus 6 choose 4. Okay. You can check. Okay. 1 plus 20 is equal to 6 plus 15. Okay. And then the theorem says that if you have such a binomial identity, you can solve the weak symmetry rating in at most 3 rounds, which is of course quite weird, taking into account that their bound is n to the n. And here's a constant 3. Not only is much smaller, it is a constant independent on n, which is also something which shouldn't be happening. Right? Usually if you can solve things for n processes, the complexity should depend on n. In fact, we don't know if it does or not. We only know that for certain special number values of n, you can actually do it in 3 rounds. So 6 is such a value, 15 is another one. We don't know for which n's such identities exist. They don't exist if they're prime power. Obviously they shouldn't, because that's not solvable, right? But that you can check by just divisibility by p. But we don't know much about it at all. It's just, well, certainly there are infinitely many of them. Any n which is divisible by 6 will have such an identity, but not much more than that. So 15, for example, also has it, and there are infinitely many which don't have it, there are infinitely many which have it. Okay. And this is the thing. Because the reason how this works may be, so this is quite strange, what's going on here. And the rough idea of how this goes is that if you have such a binomial identity, then you can use Sperner's theory. Well, it's a different Sperner than many people in topology know. There is another theorem from finite set theory, which I could go into detail, but I won't, which allows you to merge sets. Because what this identity means, it means that if I look at the set with n elements, and I look at all the subsets with 0 elements, with A1 elements, and so on, AK elements, there are equally many of those with cardinalities, prescribed cardinalities 0, A1, and so on, AK, as those with prescribed cardinalities 1, B1, and so on, Bn. And that's turned out to be the condition you can use to eliminate this cohomological abstraction of existence of such labelings, but it's not a priori clearly sufficient, it's just necessary. Okay. So if you have such a binomial identity, then you find certain bijection between families of sets. And then you have to find certain families of simplex passes in the subdivisions using this matching. So it gets quite technical. So there is a write-up which is about 50 pages of how this works. And unfortunately there is no improvement inside of how to get it simpler. But it's much simpler than what Castaneda writes, and it's also explicit because it does it for the third subdivision. And yeah, well, so probably I shouldn't get into the technical details at this point. But roughly speaking, you have to work with the simplicial structures and some sort of a strange matching theory on these graphs which arise in iterated subdivisions of the standard chromatic. So basically the whole thing is reduced to take the iterated chromatic subdivision of the simplex, takes the dual graph, and then there are some, try to understand the matching theory of that, under the condition that this cohomological abstraction is zero. So this is just so it seems like nobody knows what to do, certainly not people in received computing. They don't even know what it means, because it's like being shell-shocked. Because first you have a task, and then somebody else proves, well, you can actually solve it for prime powers, but for not prime powers, for prime powers it is not solvable, and for not prime powers it is solvable. Okay. So in particular, it just means the following: For 6 processes, so here's the thing, if you have 6 processes, there is a distributed algorithm, distributed protocol to solve the weak symmetry breaking. We don't know what it is. Okay, so these guys, well, it's no wonder they didn't know, because they had bound of 17 rounds, and it was like an existence. We have a bound of 3 rounds. So in other words, we know that it exists. We know that 6 guys can do something, 3 steps, the read, write, read, write, read, write, and then they decide. We know that it's possible, but we don't know how. Not in a natural language. Because what happened here is that we translated it into the simplicial context, and then we found some complicated assignment of labels by some other means, but it's millions of the 16 millions, I think, of these values. So the protocol would be like that. I look at what happens, and then I consult the table with millions of entries, and if I see 0, I decide 0, if I see 1, I decide 1. That's not what people in institute computing call a natural protocol, right? So actually, one of these things, it actually caused a shift of paradigm in the whole talk about complexity of the protocols, because now people ask not just for solving, but also, do they want a natural protocol? Do they want existence? Do they want constructive? Because this is constructive. It's not an existence proof. Okay, we're not using middle values theorem or anything. We're actually constructing things, but just the combinatorial complexity is so high that you cannot phrase it in the natural language anymore. You just prove that a certain assignment of values to vertices in simplicial complex exists. And it's up to them to phrase it in the protocol. And we're talking about only 6, but this is for infinitely many values, of course, the same. Right. And another thing is quite strange, people didn't expect this, and in fact it's not unlikely, I'm not sure, I'm kind of depending on the even day or odd day, what is the actual correct bound for the complexity, because we only get it for 3 rounds for certain values, for certain specific values. And it may well be that the complexity is bound by coefficients in a certain Diophantine equation, which is associated to n. Okay, there is a certain, you take n, you take the binomial coefficients associated to n, and then this binomial identity is just when the Diophantine equation has the solutions with 0, plus, minus 1. I just can phrase it such a way, I put all the plus 1s to the left, all the minus 1s to the right, I have an identity. But these things are co-prime, so there will be a solution to the Diophantine equation. And there's a bound on the size, the minimal, the size of the maximal coefficient minimized of all solutions. Okay, and that may well be that number is the actual bound for the number of rounds you need for solving this weak symmetry breaking task, which is also something kind of weird, not something you expect when you just start by saying, well, we have a few processes and I just want to decide on something. Can I just do it quickly? So, alright, so I think I'll summarize this as a study of this one specific task, weak symmetry breaking task, leads to the rich theory of subdivisions. Like I say, it's a combinatorial topology where a lot of structure is floating around. We know which structure is relevant and which is not relevant. We're trying to understand the relevant structure for the computational task, and we can't understand it beyond a certain point. It's too complex. However, simplicial methods can be used to design fast protocols. However, they're what I call explicit protocol or what they call natural protocol. It's a question of terminology. In general, it seems to remain out of reach even for 6 processes and certainly for other ones. So there are a lot of things to be done, both on the mathematical side and on the distributed computing side. I think I'll stop here.
Thank you very much for a nice talk. Are there any questions, comments? If not, then please. No, there is not. So if not, please thank the speaker again.